start. All right, any questions before we get started? You've had time to think about them. We're ready? Let us begin then. So we stopped learning about a bunch of different other types, and the last thing we did was capitalize a lowercase string using the wonderful numbers in the ASCII table. That was fun. So we talked about a bunch of different types, and I'd like to talk about types further today. So let's talk about how much stuff you can put in a type. All right? So here are the sizes and ranges of the basic types that we know about in C++. So the size of a type kind of controls how much information is there, more or less. So this is a table that you will eventually understand. Maybe not right now, but maybe towards the end of the lecture. Definitely by the end of this class. So an integer, our int type, is 4 bytes long. That's okay if you don't know what that word means. It's also equivalently 32 bits long. Every integer is either 4 bytes or 32 bits. That's the same thing. Again, it's okay if you've never heard that word before. Here's what's important. You can store the numbers negative 2 to the power of 31 to positive 2 to the 31 minus 1. Those are the numbers that you can put inside of an int. That's as much as it can hold. I hope that makes sense. A char really is just a tiny little number. It takes up only 1 byte of space, and it can hold the values negative 128 to 127. So there's kind of like a fourfold difference between ints, how much it can hold, and characters, how much they can hold. Those types. The size affects how much information is there. Okay? Then you got your doubles, and doubles are, the reason it's called double, by the way, is because there's also a decimal place E kind of type. The original one was called float, short for floating point number, and that was 4 bytes, and double is double the size, so it's 8 bytes. You can store a lot of numbers. You can store this tiny little number, or sorry, this very large negative number to this very large positive number with about 16 digits of precision. So you can't store many more than that, but you can store these numbers in like scientific notation is the idea. Okay, and then there's also numbers in between ints and chars. You got your shorts. That's a little bit of a smaller range. It's only 2 bytes, and I can store those numbers a little bit less, kind of like half of an int. And then you have longs, which is a funny little word, and those take up 8 bytes total. Let's make that a little bit bigger. Those are integers again. Longs can store kind of double the amount of an integer. Squared the amount, kind of thing. Okay, so that's a table that you will eventually understand. But I need to talk to you about like these words. What in the world is a byte? What is a bit? Because that's going to help us. All right, are you ready? So I'm gonna stop teaching you programming for just a second because I want to teach you about bases and base conversion. All right. So let's talk about bases, binary, bits, and bytes, so that whenever I say these words, you'll know exactly what they mean. Please yell at me if you have any questions. So the numbers that we use in math as humans are written in what's called base 10. Okay, we use the numbers, we use the digits 0 through 9. There are 10 of those, right? 10 digits total. That's why we call it base 10. 10 digits total. And we think that the reason we use base 10 in math is that because we do have 10 digits. We have 10 fingers, and that's why we chose base 10 most likely. So maybe if you were living in the Simpsons world, you would be using base 8. Okay? So yeah, all that base means, base something means that you have that many digits to work with. Okay? So for example, if you had base 5, that exists. That's a number system that exists. Base 5 has only 5 digits to work with. It has 0, 1, 2, 3, and 4. Does that make sense? Just like base 10 is going to have 0 through 9, 10 digits total. This is 5 digits total. With that in mind, binary is base 2. What digits do you have to work with? You only get 2, and you got to count up, so you get 0 and 1. Those are the digits that you can use to form any number in binary. I hope that makes sense. Any base, though. And so the idea is You only have the digits 0 and 1 to work with in binary, so the number 0 is 0, the number 1 is 1, but then when you try to add 1 to 1, you've run out of digits, right? Just like when you try to add 1 to 9, you've run out of digits, you need a new place, right? So that means that 2 in binary must be 1, 0. Does that make sense? It has to be that. And this looks a lot like the decimal number 10, but it's really 2 in binary, so I'm going to use the subscript to say what base we're talking about. So 10, 1, 0 subscript 2 is really, I'm talking about a binary number 1, 0, not the number 10. That's equal to 2 in decimal, 2 base 10. See how I'm differentiating between the bases now? I need to do that. Otherwise it's ambiguous. So yeah, every binary digit is called a bit. People thought that that was a cute word. They took this B and took this IT, which is short for binary digit, a 0 or a 1. And then a byte is 8 bits. Okay? And you can add on top of that megabytes, gigabytes. You can look into that. So here, like 1011 base 2, this is a 4-bit number. A 4-bit binary number, right? Because when you say bit, it's kind of implied that it's binary. Okay, so bytes are 8 bits long, so you get the smallest byte is 00000000, and then the largest byte is 4 ones, 11111, whatever that number is. Okay, does that make sense? So for any grouping of 8 bits is 1 byte. So 10110011 is 1 byte. Okay, that's the range of the bytes that you get. Any questions about any of this? And you do have to differentiate with those subscripts. So like 100 base 10, the number we know to be 100 is not the same as 100 base 5. This is the number 25, I think. Okay, there's a big difference. They might look the same, so I have to disambiguate with that little subscript. Okay, any questions about that before we go further? Potentially confuse you more, but I promise you'll get it. So how in the world can we figure out what 1111 is? Like, what number is that in our normal decimal system that we use in our brain? How do we convert? How do we do base conversion? Let me show you how to do that. How to go from any base to decimal. You do the power expansion, and this is going to make a lot of sense because this is all elementary school math again. So let me show you how to break down a decimal number, just in case we forgot. So remember how you were told to break down 1,234? You just look at all the different places. You look at the ones place, the tens place, the 100s place, the thousands place, all that. You say like 1,234, that's 1,000 plus 200 plus 30 plus 4. Remember doing that? And then you got a bit fancier when you learned about powers. You're like, all right, 1,000 is 1 times 10 to the third, plus 2 times 10 squared, plus 3 times 10 to the 1, plus 4. And that, you can still keep a 10 in there. You just say times 10 to the 0. See that? You got your 1s place, you got your 10s place, your 100s place. Is that all coming back to us? Yeah. So with that in mind, do you see the base in that expansion? It's really been there this whole time. This is a base 10 number. It's a decimal number. Look at what you're taking powers of. That's how you calculate what place you're working on. That works for any base to translate it to decimal. So here's a binary number, 10010. Let me do that same thing, but I'll just replace 10 to the 0, 10 to the 1, 10 to the 2 with 2 to the 0, 2 to the 1, 2 to the 2. That's the base now. All right, that's the place as well. So you usually work from right to left. So it's like this is the 1's place. It's the 2 to the 0's place. That's 0 times 2 to the 0 plus 1 times the next one, 2 to the 1 plus 0 times 2 squared. Technically don't need to write that, but just for posterity's sake, 0 times 2 cubed. And then finally plus 1 times 2 to the 4th. Remember that it starts at 0. So this is like the 1's place the 2's place, the 4's place, the 8's place. Now we use powers of 2. And so if we expand this becomes, well, 2 to the 4 plus 2 to the 1, which is 2, 4, 8, 16 plus 2. So that number is 18 in decimal, 18 base 10. Did everybody see what I just did? How I broke it down. That's a nice strategy, and this works for any base. You just take the power of the base itself. Okay? Not too bad, I hope. Any questions about that before I move on? 2 to the 4th plus 2 to the 1. I'm simplifying this up here. 1 times 2 to the 4. All these zeros go away, of course. The 1s stay. So that's 16 plus 2. All right. Now I want you to try it yourself. So get into your peer instruction groups, say hi to one another, and then please convert this 4-bit number. This is the biggest 4-bit number there is. Convert it to decimal. All right, 1111. Convert it to decimal, please, and do that expansion. You maybe want to see this slide at the same time. So let me take a screenshot of this or something. There. Now work on this for a couple minutes, and then we'll come back. Another minute or so. All right. And that is my timer. Let's come back. First of all, before we do this, can I stop doing attendance? Have we all signed in for attendance? Yell at me right now if you have not. 3, 2, 1. Okay. Thank you. Let's go back here. So what did we get? Did we cheat and look it up on Google? Exactly. So this is 1 times, you start from the rightmost bit, is 1 times 2 to the 1, or sorry, 2 to the 0, plus 1 times 2 to the 1, that's this one, plus 1 times 2 squared, plus this last one, 1 times 2 cubed, which is, you'll get good at this, 8 plus 4 plus 2 plus 1, which is 15 in decimal, 15 base 10. Is that what we got? I don't know what you mean by that. You only know how to do math as a human in base 10. That's why we're converting. So 15 base 10 is the final answer. It was 8 plus 4 plus 2 plus 1. Is that what we got? Nice. So bad news was that was the easy direction, to go from any base to decimal. To go from a decimal number to binary now, that's a bit more involved. So definitely pay attention in these next few slides. This is the harder way. So here's what we got to do. We would like to extract the binary digits from a decimal number. And so let's do that with, let's just extract the decimal digits from a decimal number first to see like what the pattern is, and then see if we can replace the base with a different base. Okay? So this is an algorithm I'm about to teach you. And it involves doing integer division, which you know how, that's a slash, right? 10 divided by 2, integer division, if they're both integers. And then it also involves this operator, that is the percent sign in C++. It's called the remainder operation, also called modulus. I'll say mod for short a lot, but this is the modulus operator. I'll write it like this, 10 modulus 2, or 10 modulo 2, 10 mod 2, I'll say. What this does is it divides 10 by 2, and the result is whatever the remainder was, whatever's left over. So 10 goes into 2 cleanly, right, 5 times. So you do the little division, like 10, 2. It goes in 5 times, and the remainder was 0, right? And the answer that the percent sign gives you back is the 0. Does that make sense? It calculates the remainder after doing division. So with that in mind, let us break down, let's extract the digits from 1,234 base 10, normal numbers, all right? You do it backwards. Here's the algorithm, 1,234. The first thing you do is worry about getting the rightmost digit. Get me the 4, please. And here's how you do it. You use the modulus. You say mod 10. And the result is the 4. Let me show you why. If you say 1,234 divided by 10, give me the remainder, the answer is, of course, 123, right? 0.4, but 4/10, remainder 4, right? That's the idea. And the remainder is what you're getting. You're getting the rightmost digit of 1,234 that way. Does that make sense? Key. Yeah, we're not even doing floating point stuff. We're just doing integer stuff right now. We're getting remainders. Yeah, no fractions involved. Remainder 4, the whole number 4. So, that's nice. And now, if I know how to get the rightmost digit of a number with this process, it would be really nice if I can convert 1,234 into 123, because then I could do the same thing and get the 3, yeah? So how do we convert 1,234 into 123? Question mark, question mark. Well, we can do integer division. Integer divided by 10. 123.4, chop off the 0.4, 123. Cool. So we can do this process all over again with the 123 now. Just put it here and do the whole thing. So now we can get the rightmost digit of 123. 1, 2, 3, mod 10, 12 remainder 3. 3 is left over. Chop off the 3 now to get 12 so that we can get its rightmost digit. And that's the process. 123, integer divided by 10. That's 12. Now work with 12. Get its rightmost digit. Now chop off that rightmost digit. Now start with 1. Get its rightmost digit. What's 1 mod 10? 1 divided by 10 goes in 0 times with 1 left over. 1 integer divided by 10. Chop off the 1. That's 0. 0.1, but 0.1, but the points get chopped off. And once you hit 0, the algorithm is complete. So you've got no more digits to extract. And every time you took a modulus, here, 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 and here, you got a digit just in reverse order. So that's how you extract 1,234. You extract the 4, the 3, the 2, and the 1, and you just reverse it once you're done. Questions about that? I claim this algorithm works to translate a decimal number into any base. You can extract not decimal digits, but binary digits, bits, base 5 digits even. Where does the base pop up in this algorithm? Do you see it? It's everywhere right here. I'm extracting decimal digits if I do mod 10 and divide by 10. If I change these to 2s, I'm suddenly extracting binary digits. Does that make sense? Yeah. That's how you do it. So this legitimately works for any base. Let's take 15 mod 10 or 15 base 10, which we know now is 1111. Let's run our algorithm and make sure we get 1111 out. Okay, we convert it to binary. So we start 15, oops, and we're going to extract the rightmost bit, binary digit. So I'm going to do modulus by the base you're converting to. Repeatedly divide and take the modulus by the base you're trying to convert to. 15 mod 2 is what? It can only be 0 or 1. It's an odd number, so it doesn't go in cleanly. There's one left over. That's how you do it quickly. And then I want to, this is the rightmost bit of 15. That's correct, right? It's got to be all ones, so that's good. Then I want to chop off this 1 in binary. I want to shift away the 1 in 15. So I'm going to integer divide by 2. And that's going to give me, what's this answer? Yeah, it's 7, because it's not 8, it's not 16, it's 7.5, chop off the 0.5. Good. And now I work with 7. I extract all the bits of 7. I shifted away the rightmost bit. Now I have 1111 left to work with, technically. We're going to see that that is the case. Right? So 7, get its rightmost bit, mod 2. Again, it's odd, so 1. Shift away that 1. 7 integer divided by 2. That's 3.5, so 3. Integer division always, right? Now extract the rightmost bit of 3. 3 mod 2. Odd again, so 1. Shift away that 1 out of it. So 3 integer divided by 2. That's just 1, because it would be 1.5 normally, right? Then take the 1, extract its rightmost bit. 1 mod 2. Goes in 0 times with 1 left over. 1 integer divided by 2. Shift away that 1 so that I can work with the remaining bits. Now I hit 0, and the process is complete. I don't include the 0. Okay, so every time I took a mod, I performed the modulus operation, I got a number, I got a bit, a binary digit, in reverse order. This is the rightmost bit, second to rightmost, right? So you kind of read it that way. But in our case, it's all 1, so it doesn't really matter. So 1111, base 2, that is what 15 is. So 15 in decimal is equal to 1111 in binary. That's the algorithm. Question? This first one? So it's always, we're trying to extract the rightmost digit in some base. So if I want the 4 out of 1234, this is the process. I would like to extract the 4, and the way you do it is mod the base. So if you divide by 10, 1234, you get 123, but 4 is left over. Does that make sense in decimal land? So it's the same thing in binary land. You just mod by 2 now, and you end up with 1. And that is the rightmost bit of that number if you were to convert it to binary. Okay, so what is just the remainder of 15 divided by 2? Yes, 15 divided by 2, what's the remainder? That's what the percent sign does. It gives you that remainder. Another question? For bigger numbers, are you able to create a loop back? Oh yeah, we haven't learned about loops yet in this class, but if you were to convert this to code to do the conversion, yeah, you would definitely do a loop, because it is the same thing over and over again. Yeah. Another question. Great question. Here's my next question for you. Please convert 117 in decimal to base 5. Wow. So, what are the base 5 digits? 0, 1. You get 5 of them. 2, 3, and 4. You stop at 4. 5 is not part of base 5. All right, so do that conversion. I care about you being able to convert between any base. Here's the process. I'll give you 3 minutes for this one. Use the calculator on your computer. (117) base 10. It's always you're converting from decimal to a base, or a base to decimal. If you want to convert from one weird base to another weird base, make a pit stop in decimal land. So what are you going to mod by? What are you going to divide by? Not binary, we're trying to convert to base 5. I'm pretty sure Windows Calculator has this ability. It doesn't. That would be silly. Give me programmer calculator. Hee hee. I have a feeling. Yeah, I see. If you go to the programmer version of the calculator, you get the percent sign. Oh yeah. You click here, go to programmer. All right. Do we need more time? Are we still working on this? I can't tell if silence means yes or no. All right. Take another minute or so. Remember that you get the digits in reverse order. And I've also taught you how to check your answer, haven't I? How to go the other way. All right, time is up. Let's talk about the process. So, I start off with 117 base 10. What do I modulus by? I'm converting to base 5, so it better be 5. And this makes sense because what are the base 5 digits? So it's 0 through 4. What are the only possible remainders after dividing by 5?
1, 3.
0 through 4. You can't get back 5 from mod 5 because otherwise it would go in another time, right? So that's how you can check yourself. Like, that was the right modulus. So what is this? What's the answer? It's 2? Yeah, I think it is 2. But there's ways of checking ourselves. I'll just cheat. Oh, man. This updated itself. Okay, let me fix this. Configure the default to be not that, but this, first of all. Save. Then, when we go to this one, make it pretty looking. I think I had it. This one? No. This one? We'll try that one. Alright. Now I can go here. Did I install Python? We'll see. I can check it in not C++, but in Python very quickly. So 117 mod 5, that is 2. Cool. And then, so that's the rightmost digit of whatever this is, whatever the answer is. Rightmost base 5 digits. So now I want to shift away that 2 out of 117 in base 5 land. So I'm going to integer divide by 5. What was that answer? .4, so chop off the 0.4, it's just 23. And now I want to extract the base 5 digits out of 23. What's the rightmost base 5 digit? 23 mod 5. The answer better be 3, because 5 goes in 4 times to make 20, and then 3 left over, right? 23 integer divide by 5. Like I just said, it was 4 times. And then we want the base 5 digits of 4 now. What is 4? What's the rightmost base 5 digit of 4? So 4 mod 5 goes in 0 times with 4 left over. 4 integer divide by 5 to shift away that 4 and see if I have any extra work to do. Well, that answer is 0, so I'm done. And so every time I took a modulus, I got a digit in reverse order. So the final answer is 432 base 5. 117 is 432 base 5. Notice that I'm not saying 432, because it's not, right? It's 432 base 5. And we can check this if we're not confident. I have taught you how to check this. How do you go from this to decimal again? Well, it's 2 times 5 to the 0 plus 3 times 5 to the 1 plus 4 times 5 to the 2, right? So that's 4 times 25, which is, what is 100, isn't it? 4 times, this is Python, by the way, it's not C++. 4 times 5 squared, that's 100. Plus 3 times 5 is 15. Plus 2 times 1, that's just 2. That's 117. So it checks out. We made sure that we didn't mess up. Any questions about this? This algorithm works for any base. Yeah.
Did you get 2 for the
I just divided 117 by 5 and found the remainder. So 117 integer divided by 5 goes in 23 times. 23 times 5 is 115. So there's 2 left over if I try to divide by 5. That's remainder. Remember, it's remainder. Does that answer your question? Good. Any other questions? So that is bases and binary and things like that. Now you know. We can go back to programming stuff now. So, look at this nice table that you now understand. First of all, ints are 4 bytes long, so that's 32 bits total. Kind of makes sense. Like the smallest integer is 32 zeros. 32 of them. The largest integer is 32 ones, kind of. Not technically true, but now you can see why it's so large and char is so small. You have 256 options. I haven't told you how to store negative numbers, but there's a way. So you get 1 byte for every character. That's 8 bits of information. 256 things total. We just pick some of those things to be negative. Okay? Doubles are stored in a weird way. We'll talk about later in the class, maybe. It has to do with precision and things. Like, there's a weird encoding for floating point numbers, but the rest of these are just integer numbers. Just 2 bytes, 8 bytes, storing whole numbers. Okay? So the table should hopefully make a lot more sense now. Okay? Any questions about any of this before I move on to completely different things? I am going to give you these slides. All right. So I would like to talk about different stuff now. Let's talk about just pieces of syntax that we're going to care about later. So let's talk about constants first. So let me make a folder for today. Get all this ready. Oh wait, I need to that. F22 code from class. And we're lecture 3 today. So I'll make a new folder for lecture 3. Go inside of it. And now let me teach you about a nice keyword in C++ called const. You can make constants in C++. If you have a type, if you have a variable, you can just say const before that to make it a constant variable. So for example, double pi equals 3.14 or something. You kind of don't ever want to be able to do this, like, oh yeah, pi is 3, right? You don't want to change pi ever. It's a mathematical thing that should not be messed with. You can't reset it, right? So we would like to have a way to make it so that this is a constant, it can't be touched. And all you got to do is say const in the front. Now pi is a constant. Pi is a const var, you can't change it. So now this line won't even compile. Let me show you. That's beautiful. So G++ const. In function int main, error assignment of read-only variable pi. So no longer allowed. So my recommendation to you is if you have a variable that should never have its value changed, make it a const so that you don't accidentally change it. It's just helpful for you as the programmer. You gain nothing in programming ability by adding const. You just keep yourself from making silly mistakes, right? If you're a wonderful programmer that never made any mistakes at all, you would never need const, but we're all human. Right? That's const. Any questions about that? Pretty self-explanatory. Use it when you can. Constant variables cannot be changed after they're initialized, so also I can't do something like this, like declare that the constant exists and set it later. That also makes no sense. You have to give it a value right at the beginning of its life. Otherwise, it's never going to get one. Okay, so that's const. And now I want to talk to you about these things called functions, because I've been saying that word a lot. Maybe you started reading about it in your book. We're going to use other people's functions. We're making the main function when we write our code. That's a thing. We're eventually going to make our own later, but we're going to use other people's functions right now. We already have been, actually. So let me show you how functions work, all right? So this is like the anatomy of a call to a function. This is a weird word, it's a weird metaphor, but let me just walk you through it. So a function is just a piece of code that you can have run a bunch of times to do the same thing, maybe with different values. To run that function, we use the metaphor call. So like we're yelling at it, hey function, please do this thing for me with this value. Every function can take 0 or more what are called arguments, because again, the metaphor is you're yelling at the thing. You're arguing to it, maybe. And those arguments control the way the functions work, okay? A lot of the time, functions give back an answer that you can immediately use. And when that happens, you pretend, or you write your code with the idea that your function call is going to be replaced with that answer. So here are 3 math functions, kind of. And let me show you how they work. So SQRT is just an abbreviation for square root. That's a function that lives in the math library, the CMath library, that I'll teach you about later. So you can call the square root function in C++ by saying square root, and then you put some parentheses around your arguments, which are comma separated. Square roots only need to know, you only need to yell at the square root function, hey, give me the square root of 2, please. So it only needs one argument. Okay. So we can ask for the square root of 2.0, and it's going to give back the answer. Okay. This function will definitely give back the answer, which is the 1.41 whatever, 1.41 blah, blah, blah. And so we can pretend that it's going to get replaced with that result, and we could just immediately see out it, for example. See out the square root of 2.0. This will get replaced after the function call gives back the answer of 1.4 something. Okay? Does that make sense? So we're calling a function. It's just a piece of code with a name that somebody else has written for us, and we can tell it what we want it to use when it does its work. So please give me the square root of 2, and then next time we can call it with square root of 5 or something, square root of 16. You can call it multiple times with different arguments. Those are the terms. Questions about that? Let me show you the others, if that's good enough. Then there is the PAL function. PAL is short for power. So if you want to calculate like 2 to the power of 3.5 in C++, you can do that with the PAL function. You say PAL, and then it needs to know, like, okay, what's the thing you're trying to take to a power, and then what's the power you're taking it to? So you need to give it 2 arguments, right? And they're comma separated. So like, please take 2 to the power of 3.5. That's how you would call that function. And then you could save the answer in a double variable or see out it immediately. It's going to get replaced with whatever the result of 2 to the power of 3.5 is. Yeah. It's just somebody else's code, and we're running it, and this is the syntax. Finally, there is the rand function, which is really fun. We'll use it a bit more later in the class, but rand is good for generating random numbers. So we can just ask it, hey, rand, give me a random number. And it doesn't need anything. It just needs to know that we called it. So rand takes 0 arguments. So you just put a parenthesis next to another parenthesis. And it will give you back some weird looking number like 18756, blah, blah, blah. And if you call it again, it'll give you back a different random number. Okay? So those are functions. They're just names. Give them a name, and then you put parentheses around the arguments. Those are the things that it needs to know in order to complete your function call. I need the square root of 2. You need to give an argument to square root. It needs to know what to take the square root of, right? POW takes 2 arguments. rand takes 0 arguments. Okay? Any questions about that? Before I show you them in action. All right. So let me show you. Some math functions first. Do I want to do that? Yeah, no, I'm going to do that later. So yeah, let's do math stuff first. Boop, boop. Let's explore the CSTDlib library and the CMath library. Okay, so you can go there. You can search for just on Google C++ CSTDlib C++ CMath, and it will take you to this website usually c++.com. You can just say C++ CMath, or you can go here and just like search through it C++ CMath. And so this is a library from the C language. We're importing it into C++. And so here's the CMath library, and it gives you a list of all the functions that live in the library, all the things that it knows how to compute for you. So it can do cosine, sine, tangent, all those nice things, hyperbolic stuff, exp, log, and it can do logarithms, natural logs, base 10 logs, all these fancy things. There's POW, there's square root, they exist. Let me show you square root. You can click on it, and you'll get some more information about it. It's like, all right, square root is a function that takes a single double argument and gives back a double. That's how you read it. Gives you back a double. You can scroll down to see a nice example of it, all that stuff. But if we want to use it, we got to include the CMath library. See that up there? CMath, to run the square root function. We get all of these just by including CMath. Isn't that beautiful? So, I don't know. Let me just show you math stuff. I don't know what to call this. Mathstuff.cvp. So if I want to do math stuff, I better include CMath. This will give me access to all these nice functions. So, see out the square root of 2.0. It gives back that answer. Okay, if I compile and run, I get my answer to some degree of precision. Okay, that's square root. I can call it. It gives me back the answer. I can print it out. Here are some others that are useful. You have the exponential function. So that's e to the power of something. That's exp of that thing. Okay? So it takes a double, gives you back a double. It returns e to the power of x. So if I want to calculate e, I could just ask for, hey, exp, what's exp of 1? Because that'll give me back e to the 1, which is equal to e. That's an easy way to get at that constant. See out exp of 1. That's e. Beautiful. Some nice numbers we know and love. Let me teach you some weird ones now. There's ceiling and floor are things that I want to show you here. So here is rounding and remainder functions. These first two you'll see a lot in your computer science career, so I want to teach them to you now. They're called ceiling and floor. That's the metaphor. Ceiling rounds up a value, floor rounds down a value. And not in the rounding way that you would think. It's just the next number or the next biggest integer or the next smallest integer. Okay? So if I had 2.15 and I took the ceiling of that number, it would give me back 3. So it's the nearest whole number that's bigger. And then floor, like, puts it on the ground, and that's just the next smaller integer. So that would make 2. So it's not normal rounding. Does that make sense? Ceiling and floor do that for you. So let me show you this. What is the ceiling of 2.15? That's going to be 3. What is the floor of 2.15? That's going to be 2. Okay? And, like, what is the floor of 2.99? Again, it's going to be 2, the next smaller whole number. It's not rounding up. Floor always rounds down, ceiling rounds up. Okay? Any questions about that? Silly words. Interesting. There is a function, though, that does the normal kind of rounding that we know and love. That's just called round. So that's this one, round. Round to nearest. That's the one we care about. So again, takes a double, single argument, what you want to round, gives back a double, that number being rounded. So if we were to run round on 2.15, it would do the normal rounding. It would give back 2. And if we run round on 2.5, then it would do the normal rounding and give it back as 3. Okay? Round to nearest number. Okay? So see out round of 2.15, and then round of just 2.5. There's my 2 and my 3. Okay? And so that is the C math library. The next library I want to show you is CStudlib, which is short for C Standard Library, from the C language. It's standard library. So back on this website, I can go up here. This is all the C library stuff. And I can go to CStudlib. And here are all the functions that live there. One of them is round. Yay. Or sorry, random numbers. What are some other ones that might be useful for you to know right now? Dun, dun, dun. Absolute value, abs, is a very useful one. Gives you the absolute value of a number. That's quite nice. So yeah, feel free to look at these library functions. People have implemented some nice stuff for you. Okay, just click on them, see some more information about them. But the next one I want to show you lives in CStudlib. It's rand. So let's talk about random numbers. Okay. If you call rand, it gives you back a new random number between 0 and some giant number called rand max. That's a constant for the library implementation. That's the biggest number it can do. So the number that you're getting back is going to be between 0 and whatever this large number is. You can assume it's very large, though. At least bigger than like 100,000 or something. So, yeah, let me let me show you just rand to begin with, and then I'll show you an issue. We'll fix the issue, and then I'll do these demos. I think there's plenty of time for that, yeah. So, let me show you rand. So rand lives in cstdlib, and if I call it cout rand, it gives me a random number between 0 and some large random max value. I can actually print out random max. That is a constant defined in the library. It's like, what's the biggest random number I'm ever getting back? I can print out random max. And then I'll just compute 3 random numbers. How about that? I just call it with nothing because rand just needs to know that it's being called. It doesn't need any arguments. So apparently rand max is this large value. Beautiful. So I'm getting back a number between 0 and that. And here are my 3 random numbers. Aren't they beautiful? Beautiful and random. So if I run this again, it should give me 3 random numbers, right? Boop. Oh, well, I guess that's possible given randomness. Let's run it again. Oh. What are the odds of that? I think they're pretty astronomical, so something must be going wrong. I'm getting the same 3 random numbers every time I run this program? Yeah, if I showed you this before, that's what it does. Let's fix that. Why would it do that? That's silly. So let's talk about randomness. So this is not a true random number generator. A true random number generator would need like a source of true randomness, like the decay of some radioactive particle or radioactive substance. That would give you randomness. On our computers, we do what's called pseudo-randomness. So numbers that are effectively random, but they're generated, okay? So what rand does is it has a very fancy algorithm to generate a random number, and it has like a starting value that it uses to generate a sequence of random numbers every time you call it. So let's say that the starting value is set to 1, and then it, from 1, computes like the next random number in my sequence is 42. Then after 42, it uses that to generate the next random number. Maybe that's 85. And then it uses 85 to generate its next random number. Let's say that's 12. And you can keep calling rand like this, and it'll do that and generate random numbers. And for most purposes, it feels random. Okay? It's got some nice mathematical properties, even though it's technically pseudo-random. Okay? The issue with our programs right now is we're not really ever changing the starting value of that random sequence. Okay? If we want it to give me a different sequence of random values, I better start off the generator with some value that is essentially random, that's different every time I run the program. Okay? That's the idea. It's called seeding the random number generator. So rand needs to be seeded so that it gives a different sequence of random numbers every time it runs. Okay? A nice number to seed the random number generator with, a number that's different every time you run the program, is the current time. That's a good idea, right? So if we just give the random number generator the starting value of the current time, convert it to a number in the special way, it's a default value for the time, then we will get a different sequence of random numbers every time because it starts off in a different place. Does that make sense? That's how that works. It's a weird idea, but just remember to seed your random number generator with the current time. That's what srand is for. Scroll back up here. srand, initialize the random number generator with some value, and the value we're going to give it is the current time, which lives in the ctime library. We call time with the argument 0. This is just something you got to memorize right now, and I can teach you why if you'd like to talk to me after class or during office hours, but here's the time function that gives you back the current time. You give it 0 as an argument. This is a weird looking type, but don't worry, just give it 0, and then it'll give you back whatever this is, but it's really just a number. It's the number of seconds since January 1st, 1970. That's the reason. It's a very interesting encoding of time, but that's how it's stored inside of our computers. Seconds since midnight, January 1st, 1970, UTC time. All right, and so that's going to change every second you run the program, and so it'll start off the random number generator in a different place. So I can say srand time 0 to seed the random number generator to give me different things every time. And if I want time, I say ctime. That's where it lives. So seed the random number generator with the current time. So it gives me different random values every time I run the program, assuming I wait a second to run the program the next time. That's a different set of 3 numbers. That's a different set of 3 numbers. Now we're getting some random looking things. Isn't that nice? And if you're not yet convinced why I'm spending so much time on this, like randomness is the basis of everything. Like if you want to write a game that's different every time you play it, you need randomness. There's a lot of ideas there. So yeah, let me give you some demos now. Let's ask the user for a number, and let's give back a random number between 1 and the user's choice. Ask the user for a number, be like, hey user, enter a number, int n, get it, and now let's calculate a number, give back, calculate, a random number between 1 and that n. So when I call rand, I get back this giant number, these giant numbers. I would like to kind of shrink it down to be a random number between 1 and n. Can anybody think of how I might do that? When I call rand, I get a giant number. How can I shrink it down? In a way that kind of preserves the randomness. Yeah, that would definitely work. So what happens, like, I can shrink this down into a range between 0 and some number. How can I do that? 0 between some number, like x, y, z. Well, it's a nice operator that gives me back a number between 0 and something, 42 or something. Technically, maybe. I don't know much about that exact one, but let's just pretend we're calling random. We're getting back a large number. We want to do something to this result to get the result between 0 and 42. I can use remainder. Is that what you're going to say? Yeah. I can mod by 43, and suddenly I get a number between 0 and 42. I'm not sure which one. It's still random. You see that? That's beautiful.
So if you don't get it under that number, then you want it again.
No, it's always going to be between these numbers. Now the issue is, all right, now we know if I ask for rand mod some number, why is that not erasing? That's confusing. If I ask for rand mod some number n, I'm getting a random value between 0, 1, all the way to n minus 1, right? But I need the answer to be between, for my program, I need it to be between 1 and n. How do I convert this range to this range? A number within this range to a number within this range. What do I need to do? This is n minus 1. Because if you do mod n, you're getting back an answer. Like, what remainders are you getting when you divide by 3? You get 0, 1, and 2. Always 1 less. When you divide by 2, you get 0 and 1 back as remainders. So how do I convert this range to this range? I don't know what I'm getting. Yeah.
Could you just increase the place that you're doing by 1 or minus 1 and then add 1 to it?
Yeah, so you can't do the add 1 here because it would still give you a value between 1 and n now. But if you got this first, oh man, I hate this bug in PowerPoint. This is new for this semester. Go away, plus sign. There we go. If I do a plus 1 after I do this rand mod n, now suddenly the 0 became the 1. The n minus 1 became the n. And now I have a value within the range I care about. You see that? No? Okay, so let me give you some examples, and it should make more sense. So yeah, this is your number minus 1. I need plus 1, and it will make it work. All right, so if I asked for... let's say I wanted a number between, let's make this blank really quick, sorry. Boop. Let's say I wanted a random number between 1 and 5. So I'd say rand mod 5, and that would give me back potentially 0, potentially 1, potentially 2, right? All the way to 4. And I want not between 0 and 4, I want a number between 1 and 5. So no matter what I got, as long as I add 1 to it, I will have converted the 0 to a 1, the 1 to a 2, the 2 to a 3. And now the range is correct. Does that make sense now? That's what you got to do. Good question. Any other questions? So yeah, it's still random. You're not sure which of these you're getting back, but adding 1 always is going to get it within the right range. So this is what you got to do. You say cout rand mod n plus 1. And I'll draw the parentheses just for fun. The parentheses do, if you don't use parentheses, it'll still do the right thing. Like this has precedence. But that's going to do it. Enter number 5. And so it gave me 2. Enter 5 again. Now it gives me 1. It'll never give me 0 because I'm always adding 1 to the result of rand mod n. Let's see if we can get 4 and 5 now. 3, 2, 2, 5. We're still going to get 4, right? But at least we got the upper end of the range. Let me try it one more time. All right. You'll eventually get 4. It's random. But that is the process. Does everybody understand what's going to happen? You're shrinking it down with the modulus to be between 0 and n minus 1. Adding 1 makes it be between 1 and n. That's the key. All right. That's fun. Last example, let's output 3 random characters. That'll be fun. Cout, what is a character but a number between negative 128 and 127. Negative characters in the ASCII code don't really make sense. So let's make just characters between 0 and 127. Okay? How about that? So cout rand mod. Let's do it as character variables. Char C1 equals rand mod. How do I get a number between 0 and 127? Mod by what? 128.
What?
The remainder can only be between 0 and this minus 1. Otherwise, it would go in another time because it was 128 left over. And so this is going to convert to a number, but the character is a number. So 0 to 127. Good enough? C1, C2, C3. Most of these random things are not going to be printable characters, but we'll just see what happens. C1, C2 right after it, C3. Let's see what we get. That's fun. Apparently, we got S, some unprintable character, and a new line. Because this is 2 new lines, so one of the random characters was a new line. That's impressive. We got T, capital D, semicolon this time. And so, yeah, SY, unprintable character. That's you can have fun with that after class. So, yeah, those are my examples for randomness. Any questions about that? All right, so let's keep on trucking. I got 2 more slides. So let's talk about string operations now, because string operations are slightly different. That's the string library. Again, you can look it up here. It's not in the C library. It is in, I think it's other. That's string, and click the string type. The functions on strings kind of look a bit different because you use the dot. Remember the dot at, all that stuff? They're not really functions. They're really called methods. They're kind of like S is an argument to the function, but you're just giving it in a weird place. But here is like a string. Let's say you have a string S equals hello or something like that. Let's make it blue again. Oh, I love PowerPoint. There we go. So I had string s equals hello. And now s is represented like this in memory. HELLO. Indices are starting at 0. 1, 2, 3, 4. Here is string stuff now. Probably the easiest string function is size. You can ask the string its size, and it's s.size. It's like a function that's acting on s itself. It's a weird kind of function call. It's called a method call. We'll talk about the real difference later, but you can just say size, click on it, like this is a function. It gives you back a number. Example, str.size. Let's do string stuff again. So string, that's the string library. And string s equals hello. I can ask for the size of the string, s.size. That's useful. That lets you know, like, when am I at the end? What's the biggest index I can use? You can do math using the size. Boop. So the size of hello is, of course, 5 characters. What are some other ones? So size is how many characters. That's a horrible Y. Chars. You also have the plus operator on strings, surprisingly. What that does is it adds the strings together in the obvious way. So if I have string s2 equals comma space world exclamation point, cout, well, let's just make a bigger string. String combination, combo, equals s plus s2, cout combo. New line. What's going to happen here is it's just going to add the characters right after each other. Take s, take the hello, take the comma space world, make a bigger string containing both of those characters, or all of those characters in order. Boop. That's a big string. Hello, comma space world. So it just adds them together. And so, let's look at combined strings, let's say. Combines the characters of those strings in order. And then we have these fancy ones in here. This is fun. So the syntax again is s dot something. Really, it's not a function. It's called a method. It's very weird. The reason it's called a method is because it acts on s itself. It acts on s. Okay. And so s.find is technically a method, just like the others. What does find do? It finds the index of a character in the string if it exists. So find content in string. There's a bunch of different ways to call find, but one of them is look for a character, please. And it gives you back its index if it's there. So it searches the string for the first occurrence of the sequence specified by its arguments. So let me show you that. This is going to, it's going to find the first occurrence of a character or a string inside of a string. And it gives back the index where it starts. Okay? So I can ask, hey, what's the index where the H is? Oops. Boop. So int index of H equals s.find the H character, please. What's the index of the first L? It's always the first one. Index of L. And then, we can look for the index of something that's not there, like Z. Let's look for Z in the characters. Okay? And again, we're looking through hello. That's the string S. So the H occurs at index 0, the first H. The first L occurs at index 0, 1, 2. Yeah, it's going to find the first one for you unless you specify otherwise. There's an optional second parameter being like start from this position. So starting at position 3, find the next L kind of thing. You can look up the docs for that, the documentation page. And then if it's not there, it gives back -1 as the index. So you can check against that to see if it was there or not. Okay? So that's find. Replace is fun. That just replaces part of a string. Let me see. I think I had a good idea last time. Let's see what I did last time. I did this. How do I want to replace hello? That's true. I could replace the whole thing, but what's the fun in that? Okay, yeah. Let's do translation. Let's convert hello in S to the Spanish hello. Hola. So I'm going to replace these 4 characters, right? The last 4 characters of S to OLA. Keep the H. Remember that S is hello. So here's how you run replace. S.replace, and then you give it 3 arguments. You say, where do you want the replacing to start? I want it to start at index, not 0, but 1. That's the first character I want to start changing. So starting at index 1, I would like to replace how many characters? That's the next argument. I would like to replace 4 characters. With what? That's the third thing. What's the string you want to replace at that starting point after chopping off that many, after length characters? OLA. Okay? So starting at index 1, replace the next 4 chars with OLA. And it's okay that it's not 4 characters you're giving as replacement. Just going to delete them first and then fill in the rest. Okay? So now if I print S, I should get hola. Beautiful. So that's what S is. It's been changed now. Find doesn't change the string. The plus sign makes a new string. Replace changes the string. All right? And then finally, substr. Substr stands for substring. Again, feel free to look at the documentation page. Generates a substring, so it makes a smaller string. Position and length, again. So starting from some index, take len characters from there and make a fancy string. And it gives back a string. Okay? It doesn't change the original one. So let's, let's extract la from hola. So string la equals S dot substr for substring. So please, because it's hola right now, we would like to take the first character starting at index 0, 1, 2. That's where the L lives. So starting at index 2, take 2 characters. That'll take the la. Oops, and I spelled string wrong. And there's my la. Okay? Any questions about these? You'll get a lot more experience with them as you use them. Please check the documentation page. And then also your book is going to walk you through a lot of these library functions as you read it. Okay? But any specific questions about these? All right. So my last question for us, before I just give you time to work on your lab, is this. I would like you to write down the answer this time, though, so please go to the written ICE page. I'll clear it out for us. Oops, I just accidentally, I think, disconnected from the... Yeah. Let me